To simulate pumping or injection, so the extraction or the addition of water volume to the aquifer can be done in the groundwater flow module through the source or sink term Q. I will demonstrate that based on one of the examples we have used in the past. So we will first of all, of course, as usual, define our region, and then I would just load the same homogeneous example as I used it in the past in the other videos. And I will run now the groundwater flow as we had it before without the well. So this is just to give us the initial condition, how the groundwater flow is, if there is not any well. So now we can take a quick look. That's y velocity, the x velocity as we know it, and the groundwater flow. So the groundwater head, the hydraulic head. So in the next step, now I will define the well. And here you see I located at column 70 and row 20. I'll give them an extraction rate. So with the minus, I'm extracting water of 0.1 cubic meters per second. Let's simply execute this one. And now I will run the groundwater flow. However, note that as my starting pressure head, I'm giving the result from the first run. Now I'm here also including the well as a source term. And I changed the output file so that we can separate the results. Again, I'm running for a very long time. Doing so, we can take a look at the results, and you already see now here the big dark dot where our well is located. So when I look at the well here and the legend, see, okay, at this, which is now the deepest point in our aquifer, the groundwater level goes down to almost 27.9. Remember that on the boundaries we originally had 30 and 29 meters. So we are way below what we had fixed here as a value. We can see how the pumping influences our groundwater level. So we can now also include an injection point. So we introduce another raster map. We say, well, at a slightly different position. So in column 80 and row 35, we'll inject water of the same rate as I'm extracting at the other one, but it could be any rate, but I just decided to use the same one. And now we'll simply combine both raster maps, so the injection and the well raster map, so that we have both points in one raster map together. And now I can run another groundwater simulation, again using our steady state without any pump or any injection. And with the source term Q now, this is the combined raster map I just generated. And we'll click for go. So this worked. And now we see directly here, I will remove the legend and plot the legend of the raster map you're actually seeing. You can see that at the injection point, the groundwater level is increasing a bit, while it hasn't been decreased that strongly on our well position. And again, similar to the experiment before, we can, for example, visualize our velocities using this quiver plot. So this is the same command as I've shown in the other video. And we now go back, we see here how from the, of course, injection well, the water is flowing away and it's flowing towards the well. No wonder there are a few big arrows which seem slightly distorted, Well, it simply is that because the velocity is that strong, that close to the well, and those arrows just seem very, very large, but it's just simply because it's so close to the well. However, all this together just gives us a snapshot. But for example, if we conduct a pumping test or we simulate a pumping test, we might want to know how does the pressure changes over time. And we can do this with a neat little possibility because GRASS GIS has then a built-in Python editor. And well, first of all, what we need to do is to just simply rename. You will explain in a second. I will define a raster map called pHat_0, which will make equal to our homogeneous result, right? Remember the result without any pumping or injection. And then I go to the Python editor. I can even allow here to open up a simple editor window. For simplicity, I will just simply copy paste what I prepared here, but I will walk you through this in detail. So if you know Python, well, most of those things is quite well to understand or simple. If you don't know Python, that's not a problem. I will walk you through this. All we need pretty much is this one, which is just another way to call our groundwater flow module. So the Python script works in simple that you pretty much tell them what kind of Python you want to use. You import the link to GRASS, which is line 4. We define a main function, and in this main function, we simply first set that we have an index e, which we set to 0. And this is because now we want to compute 10 steps. 10 steps with a time step of 1 day. So this is 1 day in seconds. Again, remember, this is not the numerical time step because the GRASS GIS flow module uses an implicit time stepping. It will choose the accurate time step for computation followed by stability laws and accuracy. So this is the time step after which we will generate an output. Okay, and we will do this for the duration of 10 days. So this while loop pretty much says, as long as this condition is fulfilled, he will execute what's written in here. And if we read from the top, our index e is 0, so it fulfills the condition because it's less than 10, and we just start running. What we do is we say, okay, GRASS GIS script, which we just imported, run a command. This is all what we're doing, and the command we want to use is our groundwater flow module. And now we're just giving all the parameters as we've used it before, with just a few changes. So, oh, and I'm just seeing that there is a mistake in the script. So we will use the unconfined top, the 0 level bladder, but as pHat, we will use, well, the pressure hat I just defined at the beginning, but actually this will change in every loop. So at the beginning, as I said, E is 0, so it will use the pressure hat _0, which is a raster map I just generated, and which is equal to the homogeneous background groundwater hydraulic head. The status is the well. Don't use injection here, just extraction through the well. Everything else is similar. And then I say for the output, well, give me a new file, which is just, for the first case, it will be pressured _1. And then in the next step, it will be pressured _2, and so on. So it will be one number higher than my current index, which means once I'm done with all that one, I'm leaving that one, I'm beginning from the top. Here, I then will use the result from the last step as new initial conditions. Anything else is familiar to you. As I said, just see that notice a short time step this time. So what this script will do is it will run the command, it will run groundwater flow module, here the bracket ends, so the command is in, and then all this is done and computed and generated the raster maps we want to know. It will increase the index by 1. So we start with 0, we do everything, we come here, and now it's 1. Though it goes to the top, it still fulfills this condition, so it will run. It will do this all for day 9, and then comes here from 9 to 10. It's not smaller than 10 anymore, so this one will finish and it's just done. And this is a function, and the function gets called here. So this is pretty much what we do here. And now I can just simply hit the run button. And you see here how the computation was done. We already done. Generated p hat 10. I can look here. We'll just disable those ones. And now here I get all my raster maps. Well, I won't import all of those, but you could if you want to. Just a few to look at. This is what we started with. So after 4 days, it looks like this. After 7 days, after 10 days, right? So seems we run here into a steady state quite quickly. Well, you see a bit of a change here. We'll really need a color bar for that. Maybe between day 4 and 10, this is more obvious. Yeah, you see a bit of a change here. But of course, this is a very qualitative result. We can discuss later how you can estimate this one more quantitatively.